Two recent papers have shed light on dark matter within our own Milky Way and cast doubt on two popular theories, Modified Newtonian Dynamics and Superfluid Dark Matter. In both of these theories, additional forces come into play to try to explain the velocities of stars within our galaxy other than simple dark matter. And both of them predict that stars should be moving vertically with respect to the galactic plane at accelerations that we do not observe, while a simple cold dark matter halo can explain those measurements. Can these theories recover? Firstly, why do we think dark matter exists at all? There are quite a few reasons, actually. The first reason, which was discovered in the 1930s, is that galaxies don't rotate at the right speeds if all they contain is the luminous matter we can see. We can tell how fast stars are rotating because they are made of mostly hydrogen. Hydrogen emits light at a very particular wavelength of 21 centimeters. And if that wavelength is shifted to a smaller wavelength, blue shifted, we attribute that shift to the star moving towards us. And if it's shifted to a larger wavelength, red shifted, we know it is moving away. We can combine all the observations of red and blue shifts of stars to determine how fast they are moving. The problem is that we see stars in the outer rims of galaxies moving so fast they should be breaking free of the galaxy's gravitational pull, but they don't. Instead, galaxies rotate almost like a record on a record player, with the outer stars moving much faster than the inner ones. We also know dark matter exists because of what is called weak lensing. This happens at much larger scales called galaxy clusters. These are groups of galaxies. Weak lensing is determined by the paths that light apparently takes versus the straight line path. Gravity bends light and so acts much like a lens, making objects appear in places other than straight line paths. A good example of weak lensing is the so-called bullet cluster. This is an example of two colliding groups of galaxies. Based on its weak lensing, we can determine the mass distribution, and we find that the mass centers are in two areas that are well outside the luminous centers. This means that the most gravity exists apart from where the most light is coming from. At still larger scales of the universe, we see the imprint of dark matter on what are called Baryonic Acoustic Oscillations, fluctuations in the density of ordinary matter, baryons, that we can observe in the cosmic microwave background, the earliest light we can see. You and I are made of baryons, and so is everything else we can see. Without dark matter, however, the cosmic microwave background would look very different. These observations put constraints on how much dark matter there is in the universe as a whole, at about 1/3 of all matter and energy. We know that dark matter are not baryons because there is actually a limit on how much baryonic matter could have formed during the Big Bang. That limit is about 5% of all matter and energy. Observations of supernovae help us estimate baryonic matter as being about 4.82%. Dark energy takes up the lion's share at 69%. The rest is dark matter. We also have strong reasons to believe that dark matter is cold, meaning that it is a slow-moving, massive particle and not some kind of radiation. With all of these observations pointing to the existence of dark matter, it is hard to argue that it doesn't. But people have pointed out a few issues with dark matter models. For example, in order to explain galactic rotation curves, dark matter models propose a kind of halo around galaxies. This halo gives more or less the right rotational speeds, but not quite. In order to solve that problem, a couple of alternatives have been introduced. The first is called Modified Newtonian Dynamics, or MOND. MOND says that dark matter is not responsible for the vast majority of observations attributed to it. Rather, as the acceleration caused by gravity becomes very, very small, gravity changes, declining more slowly. This allows stars which are very distant from galactic centers to experience a velocity that stays constant, keeping them rotating much faster. MOND works very well for galactic rotation curves, better in fact than dark matter halo models. Since we never see dark matter halos on their own without luminous matter, we can do away with them entirely. Unfortunately, it fails to explain any other phenomena attributed to dark matter. Relativistic models, which are theories compatible with Einstein's general relativity, therefore, have attempted to pick up the slack, with the most successful being Aether-Scalar-Tensor theory. This model proposes that there are a couple fields in addition to the usual Einstein gravitational field, an ether field. which looks like a four-dimensional field that points generally in the time direction, and a scalar field which is responsible for the MOND force. So far, Aether-Scalar-Tensor theory does a good job explaining lensing at the galactic scale, and it can even explain baryonic acoustic oscillations. It does not explain weak lensing very well, however, without some very finely tuned background fields that are, frankly, a bit like bending over backwards to avoid dark matter by making gravity behave exactly like it. Another theory that tries to explain galactic rotation curves better than cold dark matter theories is superfluid dark matter. The idea behind this theory is that galaxies have dark matter in a superfluid state. A good example is liquid helium. When it gets cold enough, it starts to behave in a quantum way, and all kinds of weird phenomena appear. For example, when you rotate a bucket of superfluid, a lattice work of little vortices appear instead of the whole fluid rotating. Superfluid dark matter creates an additional force similar to MOND. It's a bit like having your cake and eating it too. You get all the benefits of dark matter at larger scales like clusters in the universe, but you get the benefit of MOND at the galactic scale. Unfortunately, there is a problem with both of these theories in that they are entirely focused on representing the rotational speeds of stars in the planes of spiral galaxies. If we look at data for vertical acceleration perpendicular to the plane of the galaxy, however, we find that both these theories fail, since they apply the same rules to that acceleration as to acceleration towards the galactic center. The problem is that both theories are spherically symmetric in how they apply their additional force, but they are trying to explain phenomena that is better explained by a force that is cylindrical. Dark matter halo theories don't have this problem because they are not spherically symmetric. This will probably not spell the end of either theory, since the amount of data is very limited. We don't have enough data from any other galaxies to which we can compare. In addition, background fields can potentially save the day for MOND, since we can assume those are non-spherically symmetric. A background field is a boundary condition that we have to impose on a theory in order to solve it. Most critics of MOND choose a spherically symmetric background field, which is the simplest but not the only choice. More than once, the death knell of MOND has tolled, because some assume spherical symmetry. On the other hand, this does put a burden on both theories to try to explain away the Milky Way data. That was all for today. Thank you so much for watching. See you soon again the next day in the next video. Until then, good night.